In this lecture, we will learn how to calculate the Jacobians and what are the Jacobians, how do we write Jacobians. If you are interested to know how the Jacobians arise and what are the Jacobians, then I have already uploaded a YouTube video, YouTube lecture, where the title of the lecture is Understanding Jacobians. So you can go to that lecture, you particular that video, and you will find how Jacobians arise, what are the Jacobians, what are Jacobian matrix. But here I will simply introduce how to write Jacobian and how to calculate. So let us introduce Jacobians definition. Let U be function of x and y and v be some function of x and y. Then Jacobian of u be. Let u be some function of x and y. Then Jacobian of u and v with respect to x and y is denoted and defined by Jacobian of uv with respect to x and y. This is the standard symbol, which we read Jacobian of uv with respect to x and y, and this is denote defined by a 2 by 2 determinant where we write del u by del x, del u by del y, del v by del x, and del v by del y. So how do we write? There are two functions u and v and two variables x and y. So first take the first function and find its partial derivative with respect to x, then partial derivative with respect to y. So write here in a row. Then take the second function, find its partial derivative with respect to first variable and with respect to second variable and write in a second row. So this will form a determinant of 2 by 2, and this is called Jacobian of uv with respect to x and y. Similarly, if u and v and w are functions of three variables, similarly let u, v and w be functions of x, y and z, then Jacobian of u, v and w with respect to x, y and z is denoted by a 3 by 3 determinant del u by del x, del u by del y, del u by del z, del v by del x, del v by del y and del v by del z. Then finally del w by del x, del w by del y and del w by del z. So this is how we write determinant, so write Jacobians. And in the same fashion, if we have more variables in general, if u is function of suppose u1 is function of x1, x2 and xn, u2 be some function of x1, x2 and xn, and finally let un be some function of x1, x2 and xn, means there are n functions and n variables. Then Jacobian of u1, u2, un with respect to x1, x2, xn is defined as the n by n determinant del u1 by del x1 means the trick is same. Take the first function and its partial derivative with respect to x1, x2, xn will be written in first row. So del u1 by del x1, then del u1 by del x2, and finally del u1 by del xn. Then take the second function del u2 by del x1, del u2 by del x2, del u2 by del xn, and then take the third function, then take the fourth function, and finally in the same fashion finally take the nth function del un by del x1, del un by del x2, and thus we will find the complete determinant del un by del xn. So this n by n determinant is called Jacobian of u1 to un with respect to x1, x2, xn. This is how we define Jacobian and how we calculate. Now we will take simple examples to calculate Jacobians. As a first example, say it example 1, u is a function of r and theta, u is equal to r cos theta, and v is equal to r sin theta, or you can also take it x and y as you are comfortable with. X is equal to r cos theta and y is equal to r sin theta. Then find Jacobian of x and y with respect to r and theta. So as a thumb rule, Jacobian of functions with respect to their variables. X and y are functions, r theta are variables. So we will find this. We will find this Jacobian of x, y with respect to r theta. This is given by the determinant del x by del r, del x by del theta, del y by del r, del y by del theta. Then calculate these partial derivatives. So del x by del r is cos theta, del x by del theta is minus r sin theta, del y by del r is sin theta, and del y by del theta is r cos theta. You can open the Jacobian, so you will get r cos square theta plus r sin square theta, and taking r common we will get cos square theta plus sin square theta, and cos square theta plus sin square theta is 1, so this is r. So Jacobian of xy with respect to r theta is r. Now we will take another example. So let y1 is equal to x2 x3 by x1, y2 is equal to x3 x1 x3 by x2, and y3 is equal to x2 x3 by x1 x2 by x3. So find Jacobian of y1, y2, y3 with respect to x1, x2, x3. So write the Jacobian definition of the Jacobian. Jacobian of y1, y2, y3 with respect to x1, x2, x3. This is equal to del y1 by del x1, del y1 by del x2, del y1 by del x3. Then del y2 by del x1, del y2 by del x2, and del y2 by del x3. Then finally del y3 by del x1, del y3 by del x2, and del y3 by del x3. So find these partial derivatives and you can find it easily. So del y1 by del x1 is minus x2 x3 by x1 square. Similarly, del y1 by del x2 will be x3 by x1, and del y1 by del x3 will be x2 by x1. Now similarly find the other partial derivative. So del y2 by del x1, this is x3 by x1, del y2 by del x2 minus x1 x3 by x2 square, and del y2 by del x3 is x1 by x2. Similarly, del y3 by del x1 is x2 by x3, and then x1 by x3, and finally minus x2 x1 by x3 square. So you know how to solve the determinant, but my suggestion to this question is take 1 by x1 square common from first row, 1 by x2 square common from second row, and 1 by x3 square common from third row. So we will get 1 by x1 square, x2 square, x3 square, and then x2 x3, x1 x3, x1 x2, then x2 x3 minus x1 x3 and x1 x2, and finally in the third row x2 x3, x1 x3 minus x2 x3. So now it is easier, and you can take common x2 x3 from first row, x1 x first column, x1 x3 from second column, x1 x2 from third column. So these can be taken common. So you will, in general, you will take x2 common 2 times, x1 common 2 times, x3 common 2 times. So we will get this Jacobian of y1, y2, y3 with respect to x1, x2, x3. This is equal to x1 square, x2 square, x3 square divided by x1 square, x2 square, x3 square, and minus 1 1 1 1 minus 1 1 1 1 minus 1. So you can find the, you can see that x1 square, x2 square, x3 square are all are, these are cancelled out, and you can simply find these determinants. So this will become 4, and finally we have the answer. So now we will take another example. If u is equal to x square, v is equal to y square, then find the Jacobian of uv with respect to x and y. So this is simpler question. I should have taken it first, but anyway, let us solve it. So Jacobian of u v with respect to x and y. So I have already written the definition of Jacobian many times. So first element will be del u by del x, second element will be del u by del y, then del v by del x and del v by del y. So we have del u by del x 2x, del u by del y is 0, del v by del y del x is 0, and del v by del y is 2y. So our answer is 4xy. Now we will take a more sophisticated question. Now we will consider, this is our example 4. If u is given by x minus y by 1 plus xy, and v is given by tan inverse y minus tan inverse x, then find the Jacobian of uv with respect to x and y. So we already know how to write the 2 by 2 Jacobian or Jacobian for two functions. So Jacobian of u and v with respect to x and y is ux, ui, vx, vy. Now partial derivative of x, partial derivatives of v are easy to find, but partial derivative of u will take some space. So we will calculate it separately. So let us calculate it. So what is ux? Ux means partial derivative of u with respect to x, and I hope you already know how to calculate partial derivative 1 plus xy into 1 minus x minus y into y by 1 plus xy whole square. So this comes out to be 1 plus y square and divided by 1 plus xy whole square. Similarly, partial derivative of u with respect to y is 1 plus xy minus 1 minus x minus y into x divided by 1 plus xy whole square, and this comes out to be minus of 1 plus x square divided by 1 plus xy whole square. Now put these partial derivatives to calculate Jacobian. So Jacobian becomes 1 plus y square by 1 plus xy whole square minus 1 plus x square divided by 1 plus xy whole square, and then partial derivatives of v with respect to x. So this is minus 1 by 1 plus x square, and partial derivative of v with respect to y. So this is 1 by 1 plus y square, and you can open it. It will become 1 by 1 plus xy whole square minus 1 by 1 plus xy whole square, and that is finally 0. So our Jacobian is 0. Now we will take some more questions. So this will be our last example in this section. Let u1 is given by x1 by xn and u2 be given by x2 by xn. Similarly, un minus 1 is given by xn minus 1 by xn, and there is a relation x1 plus x2 plus xn is equal to 1. Then we are required to find the Jacobian of u1, u2, un with respect to x1, x2, xn. So let us find this. So as a thumb rule, you know that in order to find this Jacobian, you need to calculate all partial derivatives of first order for all the functions u1, u2, un. So first let us calculate partial derivative for un to have an idea how will this come. So you know that x1, x2, x3, xn sum to 1. So but there are only n minus 1 functions u1, u2, un. n minus 1 functions and variables are n. So we will take xn as a function of x1, x2, xn. Means xn can be written as 1 minus x1 minus x2 minus x3 and minus xn minus 1. So now xn is a function of x1 to xn minus 1. So we will differentiate xn with respect to all of these variables. Now take u1. So del u1 by del x1. Del u1 by del x1. So you can write u1 as uh, immediately you can see u1 is function of x1 and xn. So u1 can be differentiated with respect to both, but xn is function of x1 to xn minus 1. So we will apply chain rule. So first differentiate u1 with respect to x1, apply the product rule. So as a product rule, when you differentiate x1, it comes out to be 1 by xn. Then you differentiate xn. So minus x1 by xn square and del xn by del x1. This is what I was trying to say. So del xn by del x1 is what? Minus 1. So this will become 1 by xn plus x1 by xn square, or you can take 1 by xn square common. So 1 by xn square, and this will become x1 plus xn. Similarly, when you calculate del u1 by del x2, so x1 will remain constant and only xn will be differentiated. So this will become minus x1 by xn square and del xn by del x2. That means x1 by xn square. Similarly, if you differentiate u1 with respect to xn minus 1, del u1 with respect to del xn minus 1, finally it will become minus x1 by xn square and del xn by del xn minus 1, and it is what? It is x1 by xn square. Similarly, if you differentiate other functions uk, so uk is equal to xk by xn square. So you will get del uk by del x1 is equal to xk by xn square. Sorry, this is xk by xn. So xk by xn square. Del uk by del x2 is equal to xk by xn square, and all except del uk by del xk will be 1 by xk xn square xk plus xn. This will be for all k is equal to 1 through n minus 1. So now let us put these things in Jacobian. So Jacobian of u1, u2, un with respect to x1, x2, un minus 1, xn minus 1. So these are n minus 1 functions and n minus 1 variables. So we will get n minus 1 by n minus 1 determinant. So first will be x1 plus xn by xn square, then x1 by xn square, then again x1 by xn square, and finally this will be n minus 1 times x1 by xn square. Then you will get x2 by xn square, x2 by xn square, and x2 plus xn by xn square, x2 by xn square, and n minus 1 times x2 by xn square. Similarly, x3 by xn square, x3 by xn square, x3 by xn square, x3 plus xn by xn square, and n minus 1 times x3 by xn square. So final, let us write the final row. So final row will be xn minus 1 by xn square, xn minus 1 by xn square, this will be n minus 2 times xn, and finally we will have the last xn minus 1 by xn square, and last term will be xn minus 1 plus xn by xn square. So as a first thing, what you can do is take 1 by xn square common from all the n minus 1 rows. So you will get this is n minus 1 cross n minus 1. So take 1 by xn square common. So either take from all rows or from all common columns. So it will 1 by xn square to the power n minus 1. So we will get the Jacobian. This is equal to 1 by xn square and its power n minus 1. What are the remaining entries? That are x1 plus xn, then x1, 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 then x2, x2 plus xn, x2 and x2, and in this fashion, let me write one more row, x3, x3, x3 plus xn, and x3. Similarly, xn minus 1, xn minus 1, xn minus 1, xn minus 1 plus xn, this will be last entry. So now what can you do? We know that we have a relation x1 plus x2 plus xn is equal to 1. So take a sum of all the rows, means R1 can be written as R1 plus R2 plus R3 plus Rn. What will this yield? You can see x1 plus x2 plus x3 plus xn minus 1 plus xn. That all will come in first row in at each elementary position. So each element of the first row will become this sum and means 1. So we will get 1 by xn to the power 2n minus 2, and the determinant is 1 1 1. This is n minus 1 by n minus 1, so keep it remembered. So this, and then sorry, the first element, yes, then x2 and x2 plus xn and x2, and in this fashion x3 x3 plus xn x3, and finally xn minus 1 xn minus 1 xn minus 1 xn minus 1 plus xn. So now what you can do, take the column operations. What are the column operations? These column operations: c2 c2 minus c1, c3 c3 minus c1, and in general ck ck minus c1 for all k from 2 to n minus 1. So this all will be reduced to 0. So check what will be this. 1 minus 1 is 0. This x2 minus x2, here will be xn, this x3 minus x3 will be 0, this xn minus 1 minus xn minus 1 will be 0. So for the second column, all the elements will be 0 except the 2 by 2 second position, here will be xn. So what will remain, this will remain, this will remain in the second column, and every other entry will become 0. So let us use take the benefit of the same thing. The same will happen in all rows. In third row this will remain, in last row this will remain. So the matrix that we will obtain will be, determinant that we obtain will be 1 by xn to the power 2n minus 2 and 1 0 0 0 0, then 0 xn 0 0 0 0 0 xn 0 0, and finally the last row 0 0 0 and xn. Now you can open this determinant, and this is xn to the power n minus 2. Why n minus 2? Because this determinant is of order n minus 1. N minus 1 means there are n minus 1 rows. So first element is 1, so the rest element are n minus 2. So n minus 2 divided by xn to the power 2n minus 2, and finally you have calculated Jacobian of u1 u2 un minus 1 with respect to x1 x2 xn minus 1 to be 1 by xn to the power n. So this is how we calculate Jacobians, and how we define Jacobians. We, through this lecture, I hope you have learned how we define Jacobians and how do we find them. At the last of the lecture, I again revise that if you are interested to know how the Jacobians arise and what are Jacobians, I have a separate lecture, Understanding the Jacobians. So you can go to that lecture and understand what are the Jacobians. In this lecture, I hope you have learned how to define and how to calculate Jacobians. In the next lectures, I will discuss the properties of Jacobians. There are four important properties of Jacobians, and I will make individual four lectures with sufficient number of problems in each. So keep connected and watch the properties of Jacobians and applications of Jacobians. Thank you.